Welcome, embedded engineers. This video is part of our tutorial series on developing web dashboards for embedded devices. In this episode, we'll show you how to create a simple file manager on your device dashboard, which allows you to upload, delete, and view files. In each episode, we use different development boards to demonstrate that Mongoose works across a variety of hardware platforms. Today, we'll use embedded Linux, ESP32, and STM32H5. We will create a file manager for Linux, Windows, Mac first, and then reuse it on ESP32 and STM32. Plug the dev board into your workstation and visit mongoose.ws. Start a new design with the Mongoose Wizard, a visual dashboard builder. Select the target directory where the generated project will be stored and choose the target architecture, Linux, macOS. It will work on Windows too. Select the blank dashboard, click Next, then click Finish. Add a panel. Remove unnecessary elements. We want to see a file list. Let's have a list header that shows a file name, file size, file link, and a file delete button. Add a file upload button. Notice when we add a file upload, an API endpoint reference shows orange because the API endpoint was added automatically when we dragged an upload button. The endpoint name is upload, and endpoint type is file. It generates a /API/upload/fname URL on your device. A GET request to that URL fetches a file fname, and a POST request uploads a file fname. Let's add other necessary endpoints. A files endpoint of type custom would return a list of already uploaded files, a JSON list of objects with name and size attributes. A delete endpoint of type action would delete files. Let's add a file list itself, clone list header, and set an API endpoint for it to be files. When we bind a UI container to the JSON list, the wizard engine will replicate that container for every list entry. Change the file name to the current name reference. A special name current refers to the currently rendered list element. Set size to current.size reference. Set link to an HTML hyperlink that references the current file name. Finally, add a delete button. Set the API reference to delete endpoint and specify the parameter to be a JSON string that passes the current file name. That means that when we press a delete button, we send an HTML POST request with this JSON string in the body that will indicate which file we want to delete. Click Generate. The wizard creates a project in your output directory. Build and start the binary. We are on macOS, but exactly the same will work on Windows and embedded Linux. We can see that the file list is a mock. Try to upload a file. It doesn't work. Deleting a file does not work as well. It's time to change default endpoint handlers to the custom ones to make things work. Open mongoose glue.c where the default handlers are generated. The glue file open upload function handles file open for upload. The glue file serve upload serves an uploaded file. The glue reply files function generates a list of uploaded files. The glue action check delete returns true if the deletion is still in progress. And glue action start delete starts file deletion. Let's copy those functions to main.c, rename glue_prefix to my_prefix. And add mongoose set HTTP handlers to tell Mongoose to use our handlers. Create two variables. s_fs is a file system we are going to use, a standard C, fopen, fclose, fread, and so on. s_dir points to the directory where uploaded files will be stored. Modify the upload handlers. By default, they use the TMP directory. Use an upload directory instead. Modify reply files function. Return an array of files. Use mongoose specific %m specifier to print a list of objects using print files function. In this function, we use an mgfsls API call in a loop. In each iteration, it returns a file name in the provided buffer. We stat that file name to get its size and append the object to the list with name and size attributes. Now, the delete endpoint. Check delete always returns false, because file deletion is synchronous. In start delete, fetch the file name from the provided parameter, construct the full file path, and remove the file. Note that we do not do any validity checks for simplicity. When Mongoose starts, we add a call to make an upload directory, just in case it does not exist. Rebuild and restart the application. Start another terminal. Make sure the upload directory has been created and it's empty. Upload a couple of files. Delete a file. Click on a file link to see its contents. Great, it works on Mac, Linux, and Windows. This code will work on any system with the POSIX file system. An example of such a system is ESP32. It provides a virtual FS with POSIX API. Let's build this dashboard on ESP32. We take ESP32C6 board for this, but any other ESP32 device will work the same. Go to Settings, change the architecture to ESP32, generate code. Now we have an ESP-IDF project generated. Let's build it using Docker. Set the target to ESP32C6. Open main.c file and set the Wi-Fi credentials in a separate wi-fi.h file. As we can see, the default firmware code initializes SPIF's file system. Build the project. It takes a while to build. Flash it, specify no stub option if required, and start a serial console. Open the AP in the browser. We have a mock implementation now, where upload and delete does not work. Copy the same implementation we had on Mac Linux, but change the upload directory name to SPIFs. Rebuild and reflash the project. And now the file manager works. Let's try to implement the same on STM32 Nucleo H563ZI board. This board has no external storage, but the microcontroller itself has a built-in flash, and we will use a portion of that flash to implement a POSIX file system. Open Settings, select the board, choose Cube IDE and FreeRTOS. Click Generate to create Cube project. Open the project in the Cube IDE. Start a serial console, build and flash it. Open the AP address in the browser, and here we have our mock implementation ready. Open app freertos.c and copy the Linux implementation in it. Open mongoose.config.h and enable POSIX-fs and directory listing. Try to build the firmware. There are errors complaining about undefined structure their end. Open bare metal programming guide on GitHub, go to Templates, LFS, and Nucleo 563 project. This project implements a POSIX file system on Nucleo 563 using LittleFS library. Copy the Durant file to our codebase. Include Durant from mongoose.config.h. Rebuild the firmware. Now we see more errors complaining about missing POSIX calls to open directory, read directory, and so on. Copy the LittleFS files to our project. Open LittleFS repository and copy-paste lfs.c, lfs.h, lfs_util.h, and lfs_util.c. Copy the retarget lfs.c file. This file depends on external functions flash erase block and flash write buff, which is provided by a single header file, flash STM32h5.h. This implementation uses the end of the flash. This STM32h5 microcontroller has 2 MB flash with 8 KB blocks. We use the last 16 blocks of the flash, which is 128 KB. If we try to build this code, we get a bunch of conflicts for syscalls like _open, _write, _read, and so on. What are those syscalls? The Cube IDE uses ARM GCC compiler, and that compiler is shipped with a C library called newlib. The newlib library implements standard C functions like fopen, fclose, fread, and so on. The implementation calls those underscore functions, which they name syscalls. That allows users to override the behavior of the higher level functions. For example, in our main.c, we override the _write syscall to print messages to the UART. The _write override works because in the syscalls.c file, it is marked as weak. The LFS implementation overrides other syscalls like _open, _read, and so on, which makes it possible to bind the standard C functions like fopen and fread to litlfs. But in syscalls.c, only a few functions like _write are marked weak. Therefore, we have a conflict. The solution is to mark the rest of the functions weak in syscalls.c. Also, we need to delete an existing _write override in main.c and modify the _write override in LFS implementation. Rebuild and reflash. Now our file manager works. Congratulations! We have learned how to implement a web file manager. We can upload, download, and delete files. We also learned how to implement a POSIX file system on STM32 built-in Flash using litlfs. Hit like and subscribe if you found this useful. Thanks for watching and see you in the next video.